Okay, here is a theorem. It's theorem 3.44 in the book. And you have a function f on a closed interval ab, a real valued function, and it is continuous on that interval. Then it is uniformly continuous. All right. So if it's continuous and it's a closed interval, then it's uniformly continuous. Here's a proof. So we will prove by contrapositive. Namely, we will assume it is not uniformly continuous and then show that it is not continuous on the interval, meaning that at least will exist one point in the interval AB where it's not continuous. All right, so assume not uniformly continuous. So for this, we need to take the definition of uniform continuity and revert it. So that means that there exists some positive epsilon, such that for all the positive delta, or for all positive delta, there exists some pair xy. Let me call the points now x and y in the interval, with x minus y being less than delta, and f of x minus f of y in absolute value not being strictly less than epsilon, meaning being greater or equal than epsilon. So this here is not being uniformly continuous, because if it was uniformly continuous, then we would have had for all, and they would have existed, and such that if this holds, then this holds. All right. So if you revert those red scribbles, then you get the non-uniformly continuous. Okay. So since there is such an epsilon, then for that epsilon, find sequences, or we have sequences. Let's denote them as xn, n1 to infinity, and yn, n1 to infinity, such that xn minus yn is less than 1 on n. So we are going to take, because it's for all delta, we'll take delta, which is 1 on n. And the absolute value of fxn minus fyn is greater or equal than epsilon. Okay. So because it's not uniformly continuous, then for all deltas, you can do that. So in particular, do it for delta 1 on 1, and then for delta 1 on 2, and then for delta 1 on 3, and then for delta 1 on 4. And there will be points xn and yn, because there exists an x and y, so there will be an x and yn, such that x and y satisfy this, but also satisfies this. So the existence of these sequences is a consequence of the fact that we assumed that the function is not uniformly continuous at the point. Okay. Sorry. Is this? Okay. So now that we have these sequences, then by Bolzano-Weierstrass, they have subsequences that converge. And in particular, let's look at the sequence, subsequence xni, I going 1 to infinity, which converges. Okay, because the sequence is bounded and all xn's are in, we're talking about sequences in AB, so those sequences converge. And set C as the limit I to infinity of that subsequence. Hence, since xni is between A and B, then C is also between A and B. So the limit of x and I is in that sequence. So now let's show that, well, because of the way these sequences are constructed, if if the subsequence x and I has to go to the limit, goes to the limit C, then that must also be the limit of a subsequence y and I. Okay, that also converges. So what we want to do is I'll just put it in words, let's show that y and I 1 to infinity, has same limit. So y and I minus C, this is a quantity that we want to bound, and we want to see that it's that for every I there exists an M, such as for all i's greater than M, sorry, for every epsilon there exists an M, such that for all i's greater than M, this quantity is less than epsilon. So the way to do this is just to add and subtract x and I, which we've already shown has a limit. So minus x and I plus x and I minus C. And this by the triangle inequality is y and I minus x and I plus x and I minus C. So y and I minus x and I, by the way y and I, x and I is constructed, is less than 1 on ni, right? Because xn minus yn is less than 1 on n, so y and I minus x and I is less than 1 on ni. Okay, and that you could say is plus x and I minus c. Now, because x and I converges to x and I minus c converges to 0 and 1 on ni converges to 0, then hence y and I minus c converges, and in particular limit I to infinity of y and I must be c. So if you take these two subsequences that you've constructed, such that their difference is here less than 1 on n, and sorry, you've taken two sequences with different less than 1 on n, and then there's two subsequences. Those two subsequences must converge both to C, to the same value C. Okay, so now we're at a position where we have two subsequences that converge to C. Now let's show f is not continuous on C. So let's look at f x and I minus f of C, absolute value. And let's add and subtract f of y and I. So that's the absolute value of x and I minus f y and I plus f y and I minus f of C. And if we just reorder that, let's reorder that as fx and I minus fy and I minus, open brackets, f of C minus fy and I. So now let's use the reverse triangle inequality to say that this is greater than or equal than fx and I minus fy and I minus the absolute value of f of C minus fy and I. Okay. Now, and we have an absolute value here, sorry. So this was a reverse triangle inequality. And this is greater or equal than epsilon. Well, this is greater or equal than epsilon because this was an assumption about x and y, right? So those x and y's are greater or equal than epsilon. We have non-uniform continuity. Okay. Minus, and we could just rewrite the order inside the absolute value just for convenience, f y and I minus f of c. Okay. So, or now if I take this side and this side, I can just bring the absolute value here to the left-hand side. So I'm going to write f x n I minus f of c in absolute value plus f y n I minus f of c in absolute value greater or equal than epsilon. Okay. And epsilon is strictly greater than 0. Hence, at least one of f x and I 1 to infinity, or f y and I 1 to infinity cannot converge to f of c, because this difference here is greater than 0, and for having this converging to this, you need to be able to make this thing arbitrarily close to f of c. And for having this converging to this, you need to make this thing arbitrarily close to f of c. But this difference here is strictly greater than 0, and it's a sum of two positive things. So that's quite a neat argument at this point. Okay. So at least one of them cannot converge to c. So hence there exists a sequence that converges to C, but the function of the sequence does not converge to f of C. And hence f cannot be continuous at C. And that's it. Okay. So let's review what we did again. So we spoke about a function on a strictly closed interval AB. A real valued function that is continuous. So that means that for any point of that interval, it is continuous. Then we're actually going to show it as uniformly continuous. But the way we're showing it is by the contrapositive. So we're going to say, let's say that function is not uniformly continuous, and then show it's not continuous. So the key here is that non-uniform continuity is that there exists some epsilon where for all delta, there exists an xy where xy is less than delta, but fx minus f of y is greater or equal than epsilon absolute value. So then for that specific epsilon, we're going to find sequences xn and yn that are actually getting with elements that are getting close to each other like this with 1 on n. But still, the function values fxn minus fyn are greater or equal than epsilon. Right? So even though the points on the input to the function x and y are getting close, the points in the image of the functions are still going to be separated by epsilon. But now, since this is a bounded interval by Bolzano-Weierstrass, there exists an x and I subsequence that converges, and we can set the limit of x and I to be c. And hence, since x and I is less than a and b, c is also less than a and b. So the limit c is somewhere on that interval. Okay. Now, if the interval would have been open here, then this would have still been a less than or equal and a less than or equal, right? So even if the interval would have been open, that would have been a less than or equal, less than or equal. Okay, let me just undo a few of the scribbles on this. And now let's show that y and I 1 to infinity has the same limit. By the way, this y and I didn't actually write it, is also a converging subsequence. Converging subsequence by Bolzano-Weierstrass. Okay. So what we are doing is we're looking at the difference between y and I and c, and we're saying y and I minus x and I plus x and I minus c. We're using the triangle inequality. And then because y and I minus x and I, the way they're defined, they're less than 1 on an I, and because x and I converges to c, then y and I must also converge to the same c. So y and I minus c converges, and limit I to infinity y and I equals c. Okay, sorry, I'm fixing myself. Y and I is not a converging subsequence by Bolzano-Weierstrass because it shares actually the same indices Ni that X shares. So it's only X that determines the indices, the time indices, N1, N2, N3, etc., and it's converging, but it's actually going to pull Y and I to converge with it. So Y and I is going to converge to that C as well. And now here the trick to show that f is not continuous at that point C is to use a reverse triangle inequality that's here to see that fx and I minus f of c is going to be greater or equal than the difference between the function values at the two sequences and the difference between f of c and f of y and I. And then we can bring the f y and I minus f x and I in absolute value to the other side. So then we get this important inequality. Okay. And this shows us, so the two summands in this inequality, we've got fx and I minus f of c and fy and I minus f of c. And because these two things are non-negative, and this is greater or equal than epsilon and strictly greater than 0, then at least one of these guys, either this does not converge to f of c, or this does not converge to f of c. Okay, so one of them does not converge. This is quite a sophisticated proof, all right, to f of c. So there exists a sequence. It can be either x and I or y and I, okay, where both of the ni's were kind of determined by the x, but there exists a subsequence that cannot converge to f of c. So according to the sequential limit definition of a function, a limit of a function at a point, which is a sequential limit of the continuity of a function at a point, f cannot be continuous at c. And that's the end of the proof. Okay. Now, one last thing. Let's see where we actually use the fact that this is a closed interval. Okay. So what if this was an open interval? Okay. We know that the theorem doesn't hold there. We've seen an example that it doesn't hold there. Let's see where things break. Okay. So I'm going down the proof and I'm looking to see where did the open interval uh, break us. So we're still going to have that C is between A and B. Okay. But the thing is, C is now not in the domain of the function. So it can be that that C is at the boundary point, and we don't care about the function not being continuous at the point C, right? Because at the point C, well, if C is at the boundary point at A or B, then it's not in our domain. And this is why we actually need this. It's a subtle point, but this is why we're actually using the fact that this is a closed interval as an input to this theorem, as a precondition. All right, that's it. Thanks.